Okay guys, let's take a look at today's lesson. We're going to be looking at derivatives of trig functions. So pretty much this is pretty important memory work. It's just memory work. You're going to have to memorize the derivatives. So let me kind of go through and give you some pointers on how I remember them. Maybe that will help you to remember them. I've looked for patterns. So the first pattern that I want you to notice is I want you to look at all of the trig functions that start with the letter C. And then what do you notice about the trig functions that start with the letter C? They all have one thing in common. They all have derivatives that are negative. That's what helps me remember where the negatives go. That is very helpful to me because as you get in the midst of problems, it's fairly complex, that might slip your mind. So if you're taking the derivative of a trig function that starts with C, you're going to get a negative derivative. So that's important. The other, so I would pair sine and cosine together and thinking about them. So the derivative of sine is cosine and the derivative of cosine is negative sine. That kind of, just helps me. I pair those together in my brain. Tangent and cotangent, I pair those together in my brain because their derivatives are squares. So the derivative of tangent is secant squared and the derivative of cotangent is negative cosecant squared. So I think of those together. And then I pair cosecant and secant together, and because they have a similar pattern. Notice that the cosecant, derivative of cosecant is in its own derivative. It's negative cosecant cotangent. And the derivative of secant is secant tangent. So that's how I have memorized them over the years, is with those couple of patterns. The pattern to show me which ones are negative and the pattern to show me the form that the derivative should be in, what it should look like. And so hopefully that will help you in your memory work. Okay? And I'll talk about, I'll talk about that after I finish the lesson. Okay? All right. So let's take a look at our first example. We are asked to find the derivative of this particular y equals x squared sine x. Let's remind ourselves what rules we know so far. Everything that we do in calculus is a rule. Okay, as you see yourself, if you see yourself wandering down a path where you are making things up on how to do stuff, you need to stop. Everything is a rule. Okay, that's just the beauty of it. It's not, everything is a rule. So let's talk about the rules that we know. So we learn the power rule, right? We know the power rule. We know when to use the power rule, what to use the power rule on, and what can't have the power rule. We should know that. We know how to find the derivative of a constant. We know that. We also know how to find the derivative of e to the x, right? It's e to the x, and the derivative of a to the x is a to the x ln a. Remember, we know that. Yesterday we learned how to do the product and the quotient rule. Now those rules are big blanket rules. They're like the overarching rules. And when we look at trig problems, or any kind of derivative problem, we need to decide what rule is going to be the overarching rule that we plug into, because there will be other rules inside of it. Okay, so we look at this and we say, okay, well, I see that it's a product. My overarching rule is going to be the product rule. I'm going to use the product rule to do this derivative. And so we do our fg plus fg, first things first, second things second. And so y prime equals. We remind ourselves that the first thing is f and the second thing is g. So the derivative of f would be 2x, copy paste g, plus copy paste f. And the derivative of g, the derivative of sine, is cosine. So that's all the calculus involved. We look at it to see if there's a more simple way to write it. Okay? And really, we could factor out an x, but that's not going to make it any more simple. It's still going to be about the same size. So we don't need to worry about that. Now, if I was going to be setting equal to 0 and solving, I would probably factor an x out and work with it that way. But I just need the derivative. And so that is sufficient right there. Okay, so that's our first combination derivative. We use product rule and trig derivative rules and power rule. 3 rules. Okay? We all right? All right, let's go to our next slide. Just a couple more examples. All right, so let's look at this one. of the way. All right, so we're looking at f of x equals secant x over 1 plus tangent x. All right, so again, we step back and we look at the big picture. If you've got a fraction, then you're most likely, unless you can rewrite it, you're going to be using the quotient rule, and that's going to be the overarching rule that's going to tell you what to do. Okay, so in this particular case, we do have a fraction. Changing that would not be beneficial. You know, moving 1 plus tangent to the top really wouldn't be that helpful. So we're going to leave it as a quotient rule, and that's our overarching rule that we're going to use. So let's write down that rule. That is fg minus fg, first things first, second things second, over g squared. All right, so let's start. So f prime of x. So the formula for quotient rule tells me that I have to take the derivative of f. Now remember, the numerator is f and the denominator is g. Okay, just to remind you. So take the derivative of f. The derivative of secant is secant tangent. Okay, then we're supposed to copy and paste g, which is the bottom one. So 1 plus tangent x minus. Then we're supposed to copy and paste f. That would be secant x. Then we're supposed to take the derivative of g, which is the bottom one. The derivative of 1 is 0. The derivative of tangent is secant squared. All over 1 plus tangent x quantity squared. So that's our first run through. That's using the quotient rule. At this point, we're pretty much done with the calculus part, and now we're going to be working on simplification and trig. Okay, so first thing, and I know I hate to disappoint you, that is not in simplest form. Okay, it's just not. There's a lot of work we need to do on it. So the first thing that I would do is distribute the secant tangent. Okay, so we have secant tangent plus secant tangent squared minus secant x secant squared x, all over 1 plus tangent x. Okay, so at this point, yes ma'am. We could do that. I'm not going to do that yet because I'm going to show you. I'm going to be working with secant squared. Yes, I could make that secant cubed, but I'm leaving it secant squared for a reason at this point, and that is I need to see if I can identify any trig identities that will cause our life to be easier, to cause it to shrink. Yeah, we got several things we could do. I'm going to show you which one I chose. Now, it doesn't matter which one you do. I'm sure we will eventually get to the same place. What I looked at the tangent squared and the secant squared, and I thought, what would happen if I factored out a secant? Would that be something I could use? And the answer is yes. So let's remind ourselves now, our friends, the all those Pythag identities from last year. The one that I have memorized is sine squared plus cosine squared equals 1. And that's what I have in my head. The way that I generate the other three is by dividing. So, for example, if I divided everything by sine, I would be left with 1 plus cosine divided by sine is cotangent, and 1 divided by sine is cosecant. That would give me that one. So I don't have that one memorized. I don't cloud my memory out with that. I just write this one down and generate it. Now let's divide everything by cosine. That would give me tangent squared plus 1, and 1 divided by cosine is what? Secant squared. So looking at this scenario, can I get a tangent squared minus secant squared, and what would that be? -1, wouldn't it? If I move the secant squared over, it'd become negative, and then I'd move the 1 over, it'd become negative. So tangent squared minus secant squared is 1. So if I can factor out the secant, I can turn what's left into a -1, and that will help my case. So let's do that. F prime of x equals secant x tangent x plus, let's factor a secant out, and I'm left with tangent squared x minus secant squared x, all over 1 plus tangent x squared. All right, so we just discussed the fact, we just looked at these identities. We know that this is going to turn into a -1, okay, because of a Pythag identity. And I know you would love to do a proof and write the reasons, but we don't have to do that. I'm sorry to disappoint you. So what we have then is basically we have secant, tangent, minus secant. I'm just going to go ahead and factor out a secant and see if that helps any. That leaves me with tangent x minus 1 over 1 plus tangent x squared. Oh, so close to being able to get rid. We have a minus instead of a plus because of this negative. That negative turned this cosecant negative, so we're pretty much done. That's all we can do. This is a simplified version of this monster that we created. Okay, so it will require you to remember trig identities. Are we okay on that problem? Yes. You can't ever multiply by -1. You can factor -1 out, but then it would just turn into 1 minus tangent x, and it wouldn't help us. Okay? And in order to, we can't, hopefully we remember our algebra rules. I can't distribute this squared. This is not 1 plus tangent squared. There would be a middle term, right? 2 tangent x, and it's not going to help us get any smaller. So there are other things we should think of. This is good to be thinking of those things. They just won't help us to get it smaller. Okay? All right, so let's take a look at the last problem up here. Let's kind of walk through it. So this one says, on a sunny day, a 50-foot flagpole casts a shadow that changes with the angle of elevation of the sun. Okay, so the scenario is the shadow is changing with the angle of elevation of the sun. Okay? Let S be the length of the shadow and theta the angle of elevation of the sun. Okay, so I'm going to stop right here and we're going to draw. So here is a 50-foot flagpole. Okay? Okay, my sun is, there we go. There's the sun. It's casting. Here's my shadow. I said shadow is S. Okay? And theta is the angle of elevation with the sun. Now, hopefully you remember stuff about angles of elevation and depression. They're always formulated with the horizontal, never the vertical. Okay? Always the horizontal. So this would be theta. Now, if that disturbs you, really this up here is theta. But parallel lines, opposite, angles are interior angles are equal. I'm taking this as theta. I'm not going to. That is technically the angle of elevation with the sun, but I'm using this because they're equal. I want to use a triangle. Okay. All right. So there's our picture. Yes, it won't go away. All right. So find the rate. Okay, rate. What does the rate mean to us in calculus? Slope, which is derivative. It means a derivative. Okay, it's asking us to find a derivative. Find the rate at which the length of the shadow is changing with respect to theta. So the rate at which the length of the shadow is changing with respect to theta. So I need to write an equation with length, S and theta in it. That's what it says. I have to write an equation with S and theta in it. So we look at the diagram, we think, well, what kind of an equation could I write with S and theta? And hopefully when you see angle measures, you should think trig. Okay, you should think trig when you see angle measures. There are some trig identities that we can use to write equations. All right, so we have the angle measure and we have opposite and adjacent. So which would be our best candidate? Tangent. All right, so let's write it. So tangent theta equals opposite, which is 50, over adjacent, which is S. All right, so now let's see how they want us to do this. They say, find the rate at which the length of the shadow is changing with respect to theta. Well, let's think about what that means. over here on this other derivative, we found the derivative with respect to x. That's what we were doing over in this example. We found the derivative with respect to x. What does that mean? That means there's a bunch of x's in here, right? Right? We solved for the other variable. There's two variables, y or f of x and x. So it was already actually nicely done for us. It was already solved for f of x. This one isn't that way. They want us to solve with respect to theta. So that means that I need to solve for s, right? Because I want a derivative with thetas in it. With respect to theta, this tells us what they want us to put in the derivative. All right, so we need to solve for s. So let's do that. S tangent theta equals 50. Well, I need s to be by itself. So s equals 50 over tangent. I really don't want to do the quotient rule here. I mean, I know I like the quotient rule, but I would prefer to, just do a regular old trig derivative. So I'm going to change tangent to cotangent. So s equals 50 cotangent. Now, for future reference, we might consider that before we decide which trig function to use. If we had used cotangent from the beginning, we wouldn't have had to solve like that. Right? If we'd used cotangent, cotangent is adjacent over opposite, the s would have been in the numerator and we would have had less work to do. So just an FYI, and looking at how you set it up might save you a little bit of work. But that's okay. We still had fun doing that. So I have my equation now. Now I want to take the derivative with respect to theta. Now here is where I prefer the other type of derivative notation. I prefer ds d theta because it tells me what I'm taking the derivative of with respect to. That you could put s prime if you want to, but in this case I actually prefer this notation. That's what I'm going to use. I mean, you can use whichever one you want, but I'm going to use this type. And so we take the derivative of cotangent we just learned is negative cosecant squared. So negative 50 cosecant squared. All right, that's the derivative. Is that what they wanted us to find, was just the derivative? No. They wanted us to find the rate of change when theta equals 45 degrees. Okay, so we need to evaluate the derivative at 45 degrees. So one way that's written is ds d theta. Theta equals 45 degrees. You've probably seen that notation maybe on your calculator. Regular notation. Yes. Okay, so this is just a constant, right? It's just a 50. So just like if we were going to take the derivative, let's say we're going to take the derivative of 3x squared. What happens to the 3 when we take the derivative of it? It just hangs out, right? It just hangs out. It's a multiplier. That's the same thing that happens to the 50. It just hangs out and it's a multiplier. That's it. It's just a multiplier. Okay. You can do the product rule if you want to. You would get the same thing as going straight to it. I mean, because to do the product rule, you have to take the derivative of 50. And what is the derivative of 50? 0. And it would wipe that whole piece of the product rule out. So it would just be extra work for you. It's possible. You can do it. It's just extra work. It's not necessary. Okay? So are we okay now? All right. So now I'm going to substitute in the now let me ask you before we do this. When I substitute the 45 degrees in, am I going to get the same answer as if I substituted pi over 4? Does it matter which one I use? It doesn't matter, right? I need you to understand that distinction. It doesn't matter. If I put in 45 degrees, I'm going to get a particular answer. If I put in pi over 4, I'm going to get that same particular answer, right? It's not dependent. It's not dependent on what the angle measure is in right now. It's not dependent on that. Okay. So let's go ahead and, cosecant. I mean, I kind of like cosecant, but I'd rather think of sine. Sine at 45 degrees is root 2 over 2, right? So cosecant would be 2 over root 2. So negative 50 times 2 over root 2 quantity squared. Oh, yeah. I mean, it's a simplification process, sure. I mean, it's right. But I don't want to rationalize it right now. If you already had rationalized it in your head, sure, you could do that. It's going to work out in the end to be the same. So this is going to be 2 squared is 4, and root 2 squared is 2, so that turns out to be 2. So that gives me a negative 100. Now let's think about our units. Our units are feet, radians. Now that really disturbed students earlier today. So let me explain. The significance of using the theta to be 45 degrees has absolutely no significance, as I demonstrated. It doesn't matter whether we use 45 degrees or pi over 4. We're going to get the same answer. In other words, it's not dependent. This number is not dependent on degrees. Now, our default measurement in pre-cal and calculus and engineering and physics is radians. Okay, it's like a beautiful measurement. That's why we all love it. This is actually in feet per radians. They are not asking for us to be in feet per radians. They're asking us to be in feet degrees. So I actually am going to have to convert and do some dimensional analysis. Okay, I know that's troubling. We think that this is in degrees, but it's not, because it doesn't matter which type of angle measure I put in here. Now let's think about the concept. What is this rate describing? It's describing the rate at which the length of the shadow is in what measurement? Feet. The length of shadow is changing with respect to the angle measure. And our default angle measure is always radians. This is in feet per radians. Okay, how would we be able to tell if it's in degrees? Well, something would have a little degree sign on it, right? I mean, it has to have a degree sign on it to be in degrees. There would have been something up here, some other scenario that would have told us it was in degrees, but it's not. This is a side measure. Okay? Has no bearing. And that's because we would get the exact same answer if I put that. Right? Which is why I want to make sure we understood, because the students are quite confused by this concept. And, you know, especially your book loves to do this. Ask for feet degrees instead of feet radians. Okay? So, we learned how to convert last year. We know how to convert from radians to degrees. Right? We take that. It's in feet per radians. And then we multiply by, remember the radians over degrees? Remember that whole thing last year? I want the radians to go away, right? Don't I? Want the radians to go away? They're on the bottom. All right, I want, so I'm going to be left with negative 5 over 9 pi feet per degree. Now let's talk about what that means. Let's talk about what that means. What does the negative sign mean in this situation? What is happening? So it's we're talking about the length, the rate at which the length of the shadow is changing with respect to the angle measure. What is the length of the shadow doing? It's decreasing. It's getting smaller. The negative means it's decreasing or getting smaller. At this rate, at 5 pi over 9 feet per degrees. That's the rate. Okay? All right.